Today I'm going to introduce you to crime prediction in ArcGIS Pro. Predicting where crimes are likely to occur is an important activity for crime analysts and police departments more generally. By identifying high-risk areas, they can allocate resources in data-driven ways that hopefully improves community safety. We'll explore two ArcGIS tools that use existing crime data to create risk areas in the local environment, interpolation, and create prediction zones. Both tools start with point data. In this case, I'm using vandalism and criminal mischief incidents, and they transform those data layers into maps that highlight areas at elevated risk for future crimes. First, we'll use kernel interpolation with barriers to create smooth predictive surfaces based on a combined weight field that I've already created. This field incorporates the proximity and recency of incidents, giving greater weight to more recent crimes and those that occur in clusters to make its predictions. Then we'll generate prediction zones, which define discrete areas of risk using spatial and temporal parameters tailored for near-term crime prediction. When we're done, you'll have maps that look like this and this. We'll compare these outputs to evaluate how they complement each other in terms of crime prediction. So here we go. To get started, I've opened a new project in ArcGIS Pro, and I've brought into it the boundary for University City in Philadelphia. I've also brought in the footprint of Drexel University. I'm focusing on a relatively small geographic area, partly for computational purposes and partly just for ease of visualization. The reason I've brought Drexel into the map is because I know where it is, and it creates an easy visual reference for me when trying to interpret the predictions. I've also brought into the map vandalism and criminal mischief incidents for the year 2023 in University City only. And if we look at the attribute table, we see that there were 498 vandalism and criminal mischief crimes in University City for 2023, and that the crimes range from January 1st, 2023 to December 31st, 2023. Remember that in order to run an interpolation, we need a quantitative variable with a distribution. Usually that's a field measured in terms of interval or ratio level and can represent a kind of intensity field. The problem here is that each of these rows is a crime, and it's the same kind of crime. So there's no interval level measure built into this attribute table. As a result, we have to create one ourselves. I've created two separate weighting variables and then have combined them into a combined weight. The first is a temporal weighting variable, and that's a field where the most recent vandalism and criminal mischief crimes are weighted the most heavily, and the most temporally distal crimes, like the earliest crimes, are weighted the least. In fact, you can see here that a single crime that occurred on January 1st gets a temporal weight of 0, and the vandalism crimes that occurred on January 31st get a temporal weight of 1. I've created the weight this way to give greater predictive impact on the most recent crimes, because the idea is that the most recent crimes will predict future crimes in the near term. This field ranges from 0 to 1, kind of as a coefficient, again with 1 being the most heavily weighted. I've also created a distance weight based on a nearest neighbor equation. I created a command in Python to look at every crime and its nearest neighbor. The idea here is to weight crimes more heavily if they occurred in close proximity to other crimes. It sort of approximates a near repeat logic, so that crimes that occur relatively close together may have been committed by the same people, or perhaps the conditions that are predicting one crime are the same conditions predicting a nearby crime. Either way, crimes that are clustered get more heavily weighted than crimes that occur in spatial isolation. I then multiplied these weights to get a combined weighting variable that weights recent crimes and those that occur nearby other crimes more heavily than crimes that occurred in the beginning of the year and were more isolated. So we can click out of the table, and now we go into our analytical tools. To get to the interpolation, click on Tools and then type in Interpolation. And we're going to run a kernel interpolation with barriers. The input features are the vandalism and criminal mischief crimes. They're projected because I used a projected coordinate system. That's why it says that. For the Z field, this is where we specify the numeric variable. So I'm using the nearest neighbor combined weight as the prediction field. And now we have to specify two output layers. The first is a geostatistical layer that we can actually work with once it's created. So we'll type in a name that makes sense to us. Vandalism, criminal mischief, and this is going to be the geostatistical layer for the interpolation. Next, we want to specify the output raster, and we'll just copy and paste the same name and change geostat to raster. The raster layer is for visualization purposes only. The geostatistical layer is one that we can work with and manipulate and kind of change some of our prediction schemes. If we wanted to, we could create, or we could input an absolute barrier feature, such as a river or a big road or some kind of barrier that we think would interrupt the flow or distribution of crime. We don't have such a layer, so we're not going to specify an input layer for this. Under kernel function, there are multiple methods here. We're going to use Gaussian because Gaussian method allows us to identify hotspots and allows the model to use hotspots or clustered crime in its prediction. But it also allows the model to predict across a smooth area and create larger prediction areas that flow a little bit more. So it sort of gives us, in some ways, the best of both worlds for crime analysis. We're going to keep everything else the same as the defaults and click on Run. When the model finishes, it will add two new output layers to the map. The first is going to be the raster layer, which we can visualize here. The blue areas are the areas where crime is predicted to not really occur, and the red areas are those where the predictions are going to be the highest. And we can see how this works right in the middle here, in the kind of the southwestern side of University City. We see a really red heavy-duty prediction zone, and it sort of flows up and around Drexel University. So in some ways, from a predictive standpoint, Drexel serves as, at least from this analysis, Drexel serves a little bit as a barrier, even though we didn't specify the barrier level. So it does create kind of an interruption to the flow of prediction. The next layer is the geostatistical layer, which we can activate here. And I'll turn the raster off. The geostatistical layer, this is based on prediction right now, so it looks very similar to the raster layer. But if we open the geostatistical layer, we can actually work with it a little bit, and that's what makes it so interesting. So if we open this up, it comes up with a picture here. We can change the prediction method. So if we wanted to look, say, for example, at the exponential prediction method, which relies more heavily on clustered crimes or sort of examining how hotspots can influence prediction, we can change it. Doing that doesn't actually change much in terms of the output, which kind of suggests that this is a fairly reliable distribution. I'll switch this back to Gaussian. Another thing we can do is right now we're looking at our prediction output. We can actually convert this to standard error to look to see how the standard errors line up across the raster. The lowest standard errors are right in the middle in that southwest area, and they increase in the bands that are concentrically located away from it. One other interesting thing we can do is if we switch the output surface back to prediction, we can actually click anywhere on this map and get an exact prediction coefficient. So in this case, predicting here right in the middle, we've got a prediction coefficient of 0.535 or maybe 0.54. It's pretty high. If we come over here near 30th Street Station in Philadelphia, that prediction coefficient increases to 0.71. So this gives us a sense of how strong the prediction coefficients are throughout the raster. Again, the geostatistical layer is one that we can work with in real time, and it's a very helpful layer if we want to better understand how the predictions are working. Now to this project, I've also added some visual reference layers. One of them is a tessellation based on 1200 by 1200 foot grids. And if I impose that over this raster, we get a pretty clear sense of which grids have the highest risk for crime in the near term. That is sometime after December 31st, 2023. So if we were a police department, for example, we could assign more officers to the grids where the crime predictions are the highest, at least for, let's say, the next few weeks. Okay, I'm going to turn this off for now, and I'm going to turn off the interpolation layers. And now we're going to create the prediction zones. You can just access the prediction zone tool by coming into geoprocessing and clicking on calculate prediction zones. And once the tool initializes, you'll see the work window pop up here. So the input features are the same. It's going to be the vandalism and criminal mischief crimes. The tool will also produce a raster and a polygon layer as well. This is helpful because the raster is great for visualizations, but the polygon feature layer, we can actually work with that as vector data. So we can attach crimes to it. You can even attach demographic information to it or land use information to it to try to round out some of the predictions or at least contextualize them. We also have to specify a date field. So in our case, we've got one date stamped variable. You need to tell the tool when to start processing cases. So in our case, it's going to be 1/01/2023. These 6 fields here are very interesting because although the Create Prediction Zones tool does not require us to use a numeric variable to create its predictions, it does require us to specify several parameters, both temporally and spatially, so that the tool can essentially create prediction zones based on inputs we provide. So, for example, the spatial range of influence tells the tool how far away it should try to locate other crimes for clustering purposes. In our case, I'm going to specify 1,200 feet. And the reason for that is because in Philadelphia, 1,200 feet represents roughly 3 regular-sized blocks. And I also know that from previous analyses, 1,200 feet as a tolerance band works well for running the 80-20 analysis to get a better sense of crime clustering. The spatial half distance I'm going to use is 600 feet, so it's going to weight crimes that occur within 600 feet much more heavily than it does crimes that occur outwards of 600 but up to 1,200 feet. For the temporal range of influence, this is asking about the number of days the tool should go back and use for predicting near-term crimes. I'm going to specify 120 because that's roughly 4 months and that's the previous quarter. For temporal half-life, I'll specify 60. So crimes that occurred within 60 days of the end of this temporal period, they're going to be weighted more heavily than crimes that occurred within 120 days. But crimes that occurred prior to 120 days will not be factored into the predictions at all. In terms of risk calculation method, there are 2 of them. I'm going to use the cumulative, and I'm going to specify 6 risk ranges. Once we have the inputs created, we just need to click Run. Once the tool finishes, it creates 2 output layers. Again, the first one is a polygon, and in our case, we've got 6 risk ranges, and the second is the raster that I'll visualize in just a minute. But as you can see here, the highest risk for crime is the 6 area, and you can see it looks very similar to the interpolation raster. Essentially down here in sort of the southwest or west area of University City, there are relatively high predictions. And then as we move east up and around Drexel, we see high prediction risk areas here and down here. And this is 30th Street Station in Philadelphia. It's the main train station, and there's generally a fair number of crimes. I should note that on the map right now, I'm visualizing, in addition to this polygon layer, I'm visualizing the crimes that occurred in 2023. We can turn that off if we want, because the risk areas do not include these crimes. The risk areas are using those 2023 crimes to project forward. Now, it happens, of course, that the crimes on the map are occurring in large part where the highest risk areas are located, and that's certainly not an accident, especially given the temporal and spatial parameters we used. And again, I can turn on the visual reference layers, and in this case, if we turn on the tessellation, we can see what grids have the highest risk areas here. So again, a police department could assign, at least in the near term, more patrol resources or even engage in more surveillance in areas that are predicted to be risk areas for near-term crime. One of the nice things about creating a polygon file as opposed to, or in addition to, a raster is that we can work with this layer so that we can visualize just the highest risk areas and kind of clean up some of the chaos of the map. So to do that, for example, we can come under the risk range polygon and create a definition query where we tell it to just visualize the risk range that's equal to 6. And when we do that, we see that the highest risk ranges are toward the western boundary of University City. So for a police department interested in deploying resources in areas it thinks are high-risk areas for crime over the next couple of weeks, for example, they could focus their areas on these grids that overlay these high-risk areas. We can also visualize the raster as well, and we get a pretty good sense of where the prediction risk zones are based on this raster. The very light areas are the highest risk zones, and the darker areas are the lowest risk zones. One of the things we can do is look at the high risk polygon zones over the raster so that we can visualize these things together. We can also visualize the prediction zone output with the interpolation zone output. Once we do that, we can get a pretty good sense that the interpolation tool and the create prediction zones have created fairly consistent output layers, and together they're pretty complementary. The interpolation tool creates the geostatistical layer that we can actually work with and get precise measures of the predictions, and we also get to see the standard errors of those predictions if we want to. The prediction zone tool creates a polygon layer that allows us to visualize it differentially, allows us to add data to it if we wanted to. So together, these tools work very well because they can tell the story of crime risk in localized areas, but giving us different outputs that allow us to interact with those new layers in interesting ways. I hope this tutorial has helped with describing how prediction can work in ArcGIS Pro. If you want information on how I used Python to create the weighting variables, I'll link to a separate video for that in the description. Until then, thanks very much.